Hello, my name is Maria Eduarda, and in this presentation I will explain the design of an environmental monitoring system for a remote agriculture area, and mainly how this system had to be adapted when the real project conditions changed. The initial goal of the project was to create a low-cost solution to monitor important environmental variables in agriculture, such as temperature, humidity, and air quality. The initial system was based on distributed wireless IoT sensor nodes placed across the agricultural field. These sensors collect environmental data and send it through a wireless communication model to a cloud platform. In the cloud, the data could be stored, analyzed, and shown in a real-time dashboard. The user will be able to see current measurements, historical data, and alerts whenever the variable reaches a critical value. The initial solution made sense under the original assumptions. However, during implementation, the project conditions changed. The budget was reduced by 40%. The connectivity became unreliable, and maintenance had to be minimal. These changes had a direct impact on the original design. With a smaller budget, it was no longer realistic to use many sensors and expensive components. With unstable connectivity, a cloud-first and real-time monitoring system became fragile. Also, because maintenance had to be minimal, the system needed to be simpler, more robust, and more energy efficient. For this reason, the main idea was to adapt the system, not restart it. The objective of monitoring environmental conditions remained the same, but the architecture had to be redesigned around resilience, lower cost, and lower complexity. To justify these adaptations, I used the 6 Thinking Hats framework. The method helps to analyze the problem from different perspectives, without mixing facts, emotion, risk, benefits, ideas, and final decisions. Using the 6 Thinking Hats framework, I analyzed the situation from different perspectives. I started with the white hat. I focused on the facts. The budget was reduced by 40%. Connectivity became unreliable, and maintenance has to be minimal. However, the monitoring objective remained the same. Temperature, humidity, and air quality still needed to be measured. With the head hat, I considered the main concerns. Using fewer sensors could reduce the precision of the system, and having less real-time monitoring could reduce the user confidence on the data. With the black hat, I identified the risks. The original system depended too much on the cloud, so unstable connectivity could cause delays or data loss. Also, many sensor nodes would increase both cost and maintenance difficulty. With the yellow hat, I identified what should be kept. Temperature and humidity monitoring, selected air quality monitoring, digital records, and a dashboard for the user. With a green hat, I explored alternatives such as using fewer sensors in strategic locations, storing data locally, adding edge processing, and sending periodic summaries or alerts instead of continuous data. Finally, with the blue hat, I defined the final decision: a simpler and more resilient system with fewer sensors nodes, local processing, local storage during connection failures, and cloud synchronizing when internet is available. Critical values would trigger event-based alerts. So, the adapted architecture no longer depends on continuous transmission. The normal logic is to collect data, process it locally, store it when the connection is unavailable, and synchronize periodically when the call is possible. A more robust power strategy, such as battery plus solar support, can also be used to reduce maintenance needs. Of course, these adaptations involve trade-offs. By using fewer sensors, the system reduces cost and maintenance, but loses some exponential detail. With local storage, data loss is avoided during connections failures, but the device needs memory. With edge processing, the system becomes less dependent on the cloud, but the local device becomes slightly more complex. With periodic or event-based transmission, the system saves energy and reduces communication problems, but it provides less real-time data. Even so, the decision is balanced. In this context, it is more important to have a robust, affordable, and maintainable system than a perfect real-time solution that may fail often. The adapted design accepts less real-time detail in exchange for higher feasibility, reliability, and lower maintenance. To conclude, this project shows that a good plan is important, but the ability to adapt is essential when reality changes. So, the main message is adapt, do not restart. Thank you for listening till here.